Yeah, sure.
Okay, thanks. Yeah. So the reason why I've been studying StatMech so recently because I've promised to give a talk on thermodynamics to some physics people locally.
Mhm.
And part of the reason why I give talks is because I want to learn the subject well enough and be able to motivate it to, yeah, I think teaching is the best way to learn something sometimes.
I
Yeah, so I've
see.
been spending quite a lot of time understanding the nuances, like um I spent some time on the Legendre transform, and recently I've been studying the um Laplace multiplier for the distributions. So it turns out you can derive the canonical and microcanonical probability distributions, like the Boltzmann distribution, from from maximizing the entropy with respect to some constraints.
Mm-hmm.
Yeah. So perhaps if you think of the oh wait, hold on, give me a moment. My keyboard isn't connected. Let me just connect it. Mic test. Okay, yeah, sorry about that.
Yeah,
So
I can hear you.
let's say I if I the Boltzmann entropy is defined as which is a function of all the probability distributions, and you can think of this probability distribution as a vector of sorts. Then you can define it's defined as a pi ln p
Right.
I, and um wait, my screen is sharing, right? Okay, yeah, and if you maximize this entropy with respect to certain constraints, and the constraints, for example, for the micro canonical, it will be the constraint that the sum of probabilities is equal to one. Basically, that's the yeah. I mean, because you want probability to sum to one, and for the canonical ensemble, it will be two constraints. The first one being the sum of probabilities is equals to one also, but the second one being that the average energy. So EIPI equals to some constant that you set. And it turns
Hmm.
out that if you maximize this with respect to these constraints, the canonical ensemble, the constraint gives you the is simply just this one over the number of number of states there are, I being so these are I in the micro states, right? The index is over the micro states. And for these two, it gives you pi equals to e to the minus. Okay, let's say e to the, I'll just put lambda over here, representing the 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 uh is it the what's the word again? It starts with L. Um Laplace? No.
So,
Lagrange, yeah. Lagrange.
yeah, Lagrange multiplier.
Lagrange multiplier over sum of all the e to the ei, and this lambda can be determined by the second constraint. So okay, so to be specific, this gives you that, and then if you substitute this back into there, then um this constraint gives you um basically it determines lambda. So in some sense, the choice of average energy that you want to constrain your system to determines the temperature. Oh, sorry about that, my alarm. Yeah, the choice of average energy determines your temperature, your inverse temperature. And yeah, so I've been looking at the relationships between these properties and staring at them and trying to get intuitive understanding of them.
Hmm.
Yeah.
I see. Um,
And
right.
if you substitute these back into if you substitute these back into the relations, into the entropy, then basically for this one, you the microcanonical entropy ensemble entropy, which is S equals to KB ln omega. And for this one, if you substitute it back you into this one, this equation, then you'll yield the the canonical ensemble entropy, which is if I remember correctly, is S equals to KB ln Z, where Z is the denominator here. Plus, wait, is it plus or minus? I think it's plus the average energy, the average over the temperature T, where this is the temperature is like that. So in some sense, by maximizing this entropy, you can basically derive, but by this principle of maximizing this entropy with respect to constraints, you can basically derive um all the other physical phenomenon. And it may be interesting to ask, why do we want to maximize this? Like that seems like what's the motivation for this? And it turns out the motivation for this is the answer is actually to not be arrogant. So what do I mean by that? Is it means that if we think of statistical, okay, so this goes back to a particular paper. Let me see if I can recover it. Okay, I'll get a link somewhere. But this goes back to a paper where they say, yeah, I'm just gonna quickly pull it up. This goes back to it goes back to a paper. Yeah, it goes back to this paper. I'll drop it in the chat below. But this paper is by James, right? By James, and he basically says that the reason why we maximize entropy is that the idea is that assume um assume we don't know the probability distribution pi. Assume we don't know the vector pi, right? And but assume we do know some properties of the system. For example, we know average energy, perhaps from measuring the temperature of the system. Um, then the answer would be then we do know average energy, and then now we ask the question of what do we know about other quantities? So suppose we know, what do we know about um perhaps the volume of the system or something. And it turns out we want to infer information about other quantities, but we do not want to we do not um we want to infer information about other quantities, but uh we do not want to claim we know more information than we do. So we do not we want to minimize our our claim of what we know. So if if we look at this quantity over here, ln p can be thought of as a certain uncertain. Ln p can be thought of as a um, yeah, the entire entropy formula can be thought of as how much information will we how much information do we know about the system? Wait, or is it how much we do not know? How much we do not know? Because yeah. So ln p can be thought of as the information content, and the entire entropy can be thought of as the expected information. So if we study information in information theory, right, there's a notion of if we know a particular if we know suppose we have a probability distribution p, let's say we know that it's half and one third. Let's say we know it's half and 1/4 and 1/4, right? And okay, sorry. Okay, so let's say we know that is we know there's one splits into half and half, and this half splits into 1/4 and 1/4. Sorry. Yeah. So let's say we know something like that, and let's say this is 1/6, 1/6, and 1/6. So at the moment, if we do not know which one of these branches it is, we can quantify the amount of information we have about the system. But then if we are able to restrict it to a certain branch, then we have gained some information. So the example that whole Hiroshi there's a Hiroshi,
Hiroshi agree.
yeah, Hiroshi Uguri mentioned in one of his talks is that suppose that I wake up in the morning and I know that there's a half chance that my watch, right, he wants to wear his watch in the morning. Let's say there's half chance that it is in uh his in one of his drawers. And let's say there's if it's not half, right, then the other half is split into 8 possibilities, where it's one of his pockets in his pants, let's say. So that all the 8 pockets. So if he wakes up in the morning, the first thing that he will do is he will definitely, it wouldn't make sense if he checks one of his 8 pockets, right? Because suppose that is he eliminated the possibility of one of his 8 pockets, then there's still a lot of uncertainty that the information that he gained is the differences of the two entropy distribution, the entropy of the two probability distributions. So yeah, so this is just an example of what information, what the entropy of a probability distribution tells us. That kind of tells us the amount of uncertainty that we do not know. Okay, perhaps the better word here would be uncertainty, the expected uncertainty. And uncertain. So if you wake up in the morning, the first thing you check is your drawer, because checking your drawer would reduce your expected uncertainty, which the entropy, right? It reduce your expected uncertainty by a greater amount compared to your checking one of the 8 pockets. So we want to maximize our expected uncertainty, because if we chose a probability distribution that did not maximize the expected uncertainty, we are claiming that we know more information about this probability distribution than we should. So that's the information theoretic basis of maximizing entropy. Yeah, from what I understand.
Right.
Yeah, and I might not
Yeah,
have
go ahead.
understood. I might not have explained it very well, but I can assure you that this paper does. It say we are not given the corresponding probabilities pi, but all we know is expectation value of some function f of x. On basis of this information, what expectation value of g of x? Right? At first glance, it seems impossible to solve. But then we do know that it's normalized, and we do know that this constraint, right? And so um so one must so we go down further. It is now evident how to solve our problem. In making inferences about the basis of partial information, we must use that probability distribution which has maximum entropy subject to whatever is known. So we're maximizing entropy subject to the constraints. For example, if we know the average energy, or if we know the other properties of the system. This is the only unbiased assignment we can make. To use any other information, right, is amount to having an arbitrary assumption to information which by hypothesis we do not have. So basically he's saying that if we do not maximize entropy, if we don't do this, then that amounts to basically adding some additional constraint. Like for example, if if for the microcanonical ensemble, right, instead of all of it being equal distributions, suppose one of them we claim to be twice of the others, right? We're claiming that we know more information because this amounts to adding perhaps a condition that says that Pj or some specific like P5, right? P5 is twice of all the other probability distribution, maybe P4 or so on. So if we do not maximize the entropy, we are basically putting arbitrary constraints on on this, and that's claiming more than we know. So this is the most sensible, the baseline constraint that we have, right? Because the probability must sum to one. But perhaps if we claim that we know the average energy, then that's information that we can know, right? And that's why it's fair to impose that on our probability distribution. But yeah, but if we do, and that's why we want to maximize entropy, because if we do not do that, then we're saying that, oh, we know more information three, information four, right? Constraints are information on the PIs, and that is arrogance, because we are claiming to know more than we do. Yeah, so that's about it for at least what I've been studying recently. Yeah, if you guys want, I can also talk about the Legendre transform. Are you guys interested in that?
The Legendre.
Yeah.
What would you talk about if you were to talk about it? Like
Um,
there.
I'll talk about motivating it. Basically, it's a representation of a function. I'm not sure if you watched the video I recently put out, but it's a representation of a function in terms of slope.
Right.
So the Fourier one is in frequencies, right? But the Legendre transform is in slope.
Mm,
Or you want to start sharing about what you have?
yeah, I mean, like, I as usual, I don't really have much to share. But maybe I'll talk about that first. But yeah. So the thing that let me just like briefly talk about what I had to talk about first, because
Sure,
it's
sure.
really not that complicated. Um. So. Well, so I guess the key idea. So like with thermodynamics and all that. From my point of view, I always try to distinguish the actual physical theory and the information theory part.
Hmm.
Because information theory is just applied math. Um, but in the physical theory, there's physics ideas, and I think that's actually pretty important. Um, the physics ideas in physical theory is as follows. Um, so there is a notion that you can, if you have the exact quantum state of your system, if of your quantum system, which you can write as a density matrix, you also have an inexact density matrix called rho inexact. Um, and these each have pros and cons. The exact so there's pros and cons. The pro of the exact density matrix is that it's exact, but the con is that you can't calculate it. Um, on the other hand, you have the inexact density matrix. The pro is that you can actually calculate this one. But the con is that it's inexact. So as it turns out, these are rho inexact is roughly equal to the exact density matrix, in the sense that if you calculate trace rho inexact O for, then this is roughly equal, in the sense that as n, the number of particles goes to infinity, the error goes to zero to trace exact O, for a class of observables that are called macroscopic observables.
What would example of a macroscopic?
An example
Or
would be energy, volume, maybe, pressure,
I see. Wait, but
etc.
O is a quantum, is an operator that acts on a Hilbert space, right?
Yeah, but yeah, loosely you could say that.
I see.
For some things like volume, it's a little bit complicated
Mm,
because, but yeah, generally you can say that.
I
Um,
see.
like the details aren't important. The
True.
details are just details. Um, and the idea is that if you know this, you can actually calculate some things as well using this framework if you have row exact. But I'm just going to explain that row exact in many cases is just given by e to the minus beta h, where beta is 1 over kbt. Um, and you can't really prove this, because it might not always hold. But it's like a key tenet of statistical mechanics. And if you yeah, and if you take the limit where the system is really large, or if you say it in another way, if you take the limit where the heat capacity goes to infinity, then we can see that this is just equal to the microcanonical ensemble, which is just equal to um the sum over energy eigenstates um that have the energy E in some sense. But I don't really like the microcanonical ensemble.
Mm.
For like, so let me just like write like let me just complain about the microcanonical ensemble a little bit. Complaining
Sorry,
about
just now you said that in the exact partition, no, the exact row isn't impossible to calculate. But to what
yeah.
extent do you mean impossible to calculate? Like, is it for interacting theories or?
When there's a lot of particles, because like many body problems are hard. In the same sense where people say, they always go through the whole thing about saying that
Mm,
you need statistical mechanics when you have a lot of particles. This is exactly that.
I
Um,
see.
they always talk about the amount of data you would need to simulate enough of Avogadro number amount of particles. This is
See,
just equal to that. It's not really deep.
I'm
Um,
assuming that we're talking about interacting theories, right? Like for the if the Hamiltonian is
yeah,
just a free particle, then that's
Yeah, it has to
mm,
be
mm,
interacting at least. It can be interacting as weakly as you want, but it has to be interacting for you to talk about this stuff in here. Even if you have an ideal gas, usually you would assume um point particle interactions at the very least. Like billiard ball gases or stuff like that. But like these types of details are usually glossed over in statistical mechanics because we could talk about them, but it's really kind of difficult to make mathematical statements about them. So in the end, they're not really that insightful. But I'm just saying that statistical mechanics is just generally based on the idea when it comes to equilibrium statistical mechanics that you can approximate, in some sense, the density matrix of your system.
mm,
Um, and that is usually called the ensemble. You might want to go up a little bit.
I see. Cool, cool. Oh, oops. Okay.
Yeah, that is what is usually called the ensemble. So I'm just like going through terminology here. I'm going to complain about the microcanonical and ensemble a bit. Uh, for starters, if you have a finite size system, then basically your energy levels are always going to be discrete. So the microcanonical ensemble doesn't make sense. Um,
Mm,
the microcanonical ensemble only makes sense if you consider some E and E plus delta E, but this delta E is really ambiguous. So um, this is a point where that many texts on statistical mechanics gloss over, and I find this to be quite annoying. It's really ill-defined in some sense. Um, so this is why I like to talk about the canonical ensemble more and view the microcanonical ensemble as secondary. There's also
sorry,
this thing called the
what do you mean
sorry.
by delta E and delta E? I didn't really understand about the separation.
Well, as it
Mm,
turns out, if you have n particles in a box, for
mm,
example, the spectrum is discrete.
yeah.
Um, so you can't so omega E doesn't make sense.
Oh, I
It is a
mm,
very sporadic function.
I
It
see.
is
Oh,
not
so
smooth.
you like your counting of microstates to be a continuous function.
Right, you want it to be well
Okay.
behaved.
Yeah.
So in reality, what you're actually doing is you're making some assumptions. You're actually being a little bit more lenient by picking up
Mm,
states over an interval or something. But that is all just very ambiguous. It's not really ambiguous. Like if you have a concrete example, you can always do this kind of stuff. But I just like the canonical ensemble because I feel like it's the ensemble that everyone uses the most, and that is
mm,
actually relevant in real life because
mm.
the microcanonical ensemble only holds for ice systems that are totally closed off from the environment, but that never happens.
Right, right.
Um, so you can also say that the microcanonical ensemble holds if you're taking the entire universe into account.
Mm.
But you can never do that. So yeah,
Also, I just read today that bounded energy levels would yield a negative entropy. Like, yeah, it's a essential, it's a if and only if. So if your system has bounded energy levels,
yeah, that's true.
yeah. But finite size is a different concept because you can
Yeah,
have finite size, but you have infinite energy level. So yeah, cool, cool. Just wanted to add on.
yeah. I guess you could prove that, but you could note your statement essentially points out that if you have e to the beta e and e is unbounded, and beta is positive, then in this case, this operator does not have a trace.
Oh,
It does not have a well-defined trace. The trace
oh,
diverges.
that's
Um,
interesting.
um, But the thing I really wanted to talk about today was to talk about the notion of entropy.
Hmm,
Because there is already an information theoretic concept of entropy, which is all very nice. And there's the
sure.
whole second law of thermodynamics, which is basically a statement about spontaneous entropy increase. Um, but technically, the second law of thermodynamics is one of those things. It's more of a physical idea than a mathematical theorem.
Hmm.
So you can't really prove it, but you can use it physically.
Hmm.
Um,
Also, later,
so
could you segue into the three roads to entropy? Because I saw your talk, but then
oh
it was in
yeah,
Korean. Yeah, so I would love to hear the
uh,
ideas.
yeah. So like entropy, yeah. So let me just write all the things about I know about entropy. First, there's
Mm.
information entropy. Um, this is just a mathematical definition. Uh, um, then you have entropy as an adiabatic invariant.
Mm.
Technically, these are different concepts. You also have entropy um, as something that grows, or I would say entropy in the second law. You also have entropy, entanglement entropy.
Mm.
Again, there's a mathematical definition for this. Uh, so these two have nothing to do with physics. I'm just joking. They have a lot to do with physics, but they are mathematical definitions.
Mm.
So you could just study them like math. Over here you have two things that you can't really study like math. These are physical concepts. And the second law, yeah, nobody really explains the second law very well. I think the course at MIT did a pretty nice it had some pretty nice exposition. But like this is one of those things where any explanation would just be really hand waving. Um
Mm.
and it's just like ancient lore. And you should view it as such. In the case of entropy as an adiabatic invariant, this is something you can actually prove, and this is something that's actually very interesting. Um and I'm just going to sketch the proof. So what we're going to prove is that under an adiabatic process, S is conserved. So I'm just going to write this as um my point one, P1,
Mm.
I guess, proposition one. This is our P1. And before we talk about why P1 holds, I'm going to explain why P1 is useful. Because let me just write a definition. A definition is that adiabatic is equal to no heat. So from P1 and D1, you see that basically, and we use another proposition P2, which is this first law, which is dq equals dq plus dw. And so if we use P1 and D1 and P2, we basically see that, okay, just assume that dq equals 0. So assume that ds equals 0, then dq equals 0, then du equals dw. So dw is equal to partial u, partial parameters other than s. I'm just going to assume that there's one parameter and its volume. You can consider it a generalized case, but this doesn't really matter. So you can know this. And alternatively, what you can do is, I'm going to call this P3. Alternatively, you can start from P3 and D1 and P2, and you can go to P1. So now consider that you start with this formula, and then assume that dq equals 0. Then if dq equals 0, then du equals dw. Then you see that du is equal to partial u partial v s dv. So necessarily we see that ds must be 0. So we see that from dq equals 0, then ds equals 0. So we can see that we can either prove P3 or P1. And proving one of those would show both of these statements, P1 and both P1 and P3. And we see that this is useful. In the case of P3, we can realize that we can calculate the work done on a system by just calculating some partial derivatives of the energy with respect to the entropy, if we just define entropy in some sense. And for P1, this is useful because we can see whether or not a process is adiabatic based on whether or not S is conserved. And I do have to note that right now, we are only talking about quasi-static processes where the system is in equilibrium, approximately in equilibrium at every step. If you go into non-equilibrium states, then we have to do non-equilibrium thermodynamics, and we would be going outside the regime of validity of what we're talking about here right now. But what I would like to point out is that P1 and P3 are useful, and we actually prove these things. But I'm going to prove P3 instead of P1.
Do you have any any ideas to share about non-equilibrium? Because I don't know anything about it, but I would like to, yeah, it'll be nice to learn a bit.
I don't know, but one of the things you can do, you can I'm gonna write this like below what I just wrote. But one of the things you can do is you can consider you can consider your system, and you can consider environment, and you can consider the total Hilbert space as the Hilbert space is a system tensor product with the Hilbert space in the environment, and you can just apply the usual Schrodinger picture time evolution. Uh, just do the usual quantum mechanics, but with an interaction. And you always trace out env at every step. Well, not at every step, but you trace out env at the end of the calculation. So you're interested in row cis. So yeah, this is like the basic framework for thinking about things, and then you make a few assumptions about the environment, and you can figure some things out. Um, but I don't know about the subject, but it's very much
Okay.
first principles with some approximations and assumptions, as is always the case of physics. Um, but yeah, anyway, back to what I was talking about. We're going to consider P3, and P3 is the fact that du is equal to partial u partial v s dv. Well, no, it's the it is the it's this statement that the work is equal to this value. Um, right. And how to prove, I'm going to sketch. So then the first thing you do, okay, you use dw is equal to partial h partial v time average dv, and you can prove this. So this is something you have to prove first. So
H being the enthalpy.
h is the Hamiltonian.
Oh, okay, sure.
So this is P3-1, and this is a time average. And the exact definition of the time average here is some time average over some microscopic time, 10 to the minus whatever seconds. This is vague as stated currently, but like you can, if you work through the process of trying to prove this, you'll come up with your own definition. So I'm just gonna skip. And now that you proved this, what you need to do is now show that partial h partial v is equal to partial u partial vs. And what you're going to use here is the fact that partial h partial v is equal to trace over rho inexact partial h partial v. And if you use this fact, then you will see that rho inexact. And you can see that if you just input the information entropy formula as given above, this thing actually holds. So you'll be able to prove this. This is the rough sketch, but yeah, it's doable.
So the partial derivative on the right side is saying that we take the partial derivative assuming that s is constant, right?
All right.
Okay, and we want to prove that this time average is equals to this quantity over here.
Yeah. You can do it. I'm not, but I'm
Okay,
not,
sure.
um, but you just need to know that it's doable. You don't need to have to actually do it. And this is just
Sure.
for your, this is just knowledge.
Cool.
It's not helpful. Um, so yeah, that's that. And thus I have roughly explained to the best I can all the four aspects of entropy, or all the four roads to entropy that I've explained above. That's pretty much it.
That's cool. Cool. I
I mean,
guess
like, yeah, all of these topics deserves like a 2 hour lecture, but I don't have the time for that.
sure. I guess it's interesting to understand because they say heat is basically disordered. Heat is energy that you cannot get work out of, right? Basically, heat is
Right.
disordered or
Oh yeah,
non-mechanical energy.
yeah, right. Heat is non-mechanical energy. Did that definition kind of leaks into here somewhere?
Yeah, I feel like it's
So
very related to D1 because if you're and P1 and D1 because now that looking at it
yeah,
here that you stated out clearly, it's clear that if the heat transfer with the environment is zero, then because there's no disordered energy coming in and out, right? You haven't lost information to some extent, and hence entropy, which is information, is unchanged. Yeah,
right. Like you will have to define what you mean by heat very carefully.
yeah.
Um, and the usual definition of heat that I use is heat is every type of energy transfer that is not work.
Mm,
But you may, so your definition of heat essentially depends on your definition of work. But your
mm.
definition of work usually involves some notion of, so let me just make a
Recoverability.
diagram over here. So like definition of Q is basically linked to the definition of work.
Mm,
Um, but this is linked to some notions of steadiness and slowness, right? Because
mm,
um, so like if you have a gas and you're pulling a piston, um, if you don't pull it too quick, if you pull it like pulling a piston, right? It's much more
Mm,
slower and steadier than the motion of the vibrations of the molecules in the piston that convey heat. So
mm,
that's really the difference. And you can set up some scales upon which you can set some cutoff scale to differentiate between work and heat if you like.
mm. I
But
feel
that
like
is up to you. This is just a big idea.
I feel like a good definition of work would be energy that is recoverable to some extent.
Right, but that definition depends on the second law of thermodynamics, which is fine, which is totally
Mm,
fine.
mm,
But like it's all linked together and it's all kind of
mm,
vague and ambiguous. But in the realm where ordinary thermodynamics is most useful, it's not really that ambiguous. Um,
mm. Yeah, that's cool. Okay.
Yeah, like statistical mechanics has always been a very ambiguous subject. You can't really axiomatize it.
Yeah.
It's not really that helpful to axiomatize statistical mechanics. I had a phase back when I was in high school trying to axiomatize statistical mechanics. It was the most annoying thing that I've
Yeah.
ever done. It was
Yeah, I
extremely
think that's my
painful.
face right now.
Yeah, but like,
Yeah.
yeah, it's a phase that everyone has to go through anyway. If I
Mm,
mean, like, yeah, it's a rite of passage. Um, so okay. So what I wanted to do, starting today, I wanted to focus entirely on Donaldson theory, and
yay.
which is a part of math. The reason why I'm doing this, is that I find it interesting,
Mm,
because it's one of those parts of mathematical physics, and I find that it's always quite lovely to study math. Um, so but clearly there are a lot of prerequisites because none of us are really like trained in math in the traditional sense. So prerequisites that come to mind are basically a bunch of analysis, and a good place to start is measure theory.
mm,
But I feel like a lot of you might be a little bit too tired to hear about measure theory today, so maybe I'll have to postpone it to next time. But I will try to basically go through everything very speedily. Um,
yeah, sure. I'm
and
okay. I'm okay. Yeah.
yeah, and what I want to do is when I explain things, I will try to explain things um in terms of prepositions.
Mm,
So that I might not prove the prepositions, but at least you know what the flow of logic is. And I guess that's important because then all you need to do is just fill the blanks. Um, yeah. So yeah, I will do a very preposition and sketch based talk.
mm,
Um, because we don't have the time. And
sure.
as the days go by, I keep hearing the professors that I know telling me that studying advanced material in itself is very useless and that you have to actually do research. But as it
Oh.
turns out, when you do research, you only have to prove the things that are in your paper.
Yeah.
Um, Maybe there's a lesson to be learned there. I don't know, but yeah, I have my eyes set upon Donaldson theory,
Cool.
which is basically applications of gauge theory to topology, which is very
Mm,
interesting.
yeah.
And it will involve both analysis and algebra, which is also very interesting. We'll do this next time, next week's, I guess. Thank you. That was all that I had to say for today.
Cool, cool. Thanks for sharing. Yeah. Um, for Hey Yoon, you want you have anything to share? It's okay if you don't. Okay, cool,
Hmm?
cool. Yeah.
Oh yeah, that's cool.
If you're not tired, I don't mind hearing about measure theory, but yeah, that's up to you. I'm okay with anything.
Yeah, I don't know. Uh, I'm not sure how, I have to fix my blog. My blog is very old. I might have to put it into archive mode, um, and create another blog, where I can expand upon my thoughts more freely. Um, yeah, I don't know, but I feel like the current blog system is not very does not fit how my brain is wired these days, which is not always not very effective. It has to
Yeah.
evolve. So yeah, I don't know. I don't know
Yeah,
how
I
I'm gonna
understand
do
how you feel.
things.
I've always found that I'll tell myself that I want to invest a bit of time in setting up a good system. And
Right.
then I realized that I spend more time on the system than I should.
No, but the system
And
is important, right? Like I think that's a good
yeah,
thing. Um,
that's true. Yeah, I'm not sure there's a balance to strike.
yeah, I don't know. Like the whole point of writing documents on stuff you've learned is to use it as a reference of sorts. But
Hmm.
nowadays, I just feel like I could read references that other people wrote. So what's the
I
point of
see.
me writing things? I don't really know. If I find an answer to that question, that would help me a lot. Um, because yeah, I do have to keep in mind that only like a very small amount of people actually read the things that I write.
Yeah, I
So
do though. I
I
do.
don't I don't have a large enough user base so that I could cater myself to everyone's expectations of what's going to happen. So really, I don't know. I don't know what's the point. But I'll find a happy ending.
Cool, cool. Yeah, whatever fits your needs, I guess. I think that
Yeah,
the biggest biggest benefactor, is that a word, for my own notes are also myself. Like my videos that I make,
right,
like I think I rewatched my videos the most. So it's kind of funny.
right. But I guess it's always like that. But
Yeah.
yeah, huh. Well, yeah. It's all very interesting. I have no idea what's going to happen next, but it's all very interesting. Well, another thing that's also going to be important, um, will be to catalog knowledge. Because the thing with academia is that the knowledge is not readily available on the internet, um,
Hmm.
as much as other fields. Um,
I see.
so you have to create your own bibliographies using BibTeX or whatever, and
Yeah.
this is something that you should not find unimportant because you really need to do your BibTeX work. This
Yeah.
is crucial.
I personally
Um,
find that Zotero is really, really good for this. As in, I actually pay for the subscription to get more uh more storage, but I like it because it's
really,
simple.
like, what's the cost? How much it cost?
It's really affordable, I think, and it's an open source project, so I would like to support open source too. Yeah, it's free and open source, so I mean, I'm always a fan of open source work. So the thing I like about
Yeah,
it is, oh, even as integration of overleaf. So you can okay, I've never tried this before, but suppose I wanted to import
really. Oh my God,
yeah,
that's
so like
amazing.
you can do uh yeah, I can't find the place right now, but there was something I saw. Is it new file? Oh, yes, you can do this.
Oh
From
my God, that is so amazing.
I do not. Oh. Wait, let me try this. Creating. I'm doing this for the first time, by the way. So um, it could go a references.bib. Oh wow, and this is all my references, I suppose. Is it under? That's a lot though. Yeah, I think this is
Yeah,
everything.
this is really cool.
Yeah, it looks like
Yeah.
everything. There's all kinds
Oh
of
wow.
information. That's great. Yeah, so I have folders for different topics, and for each one of them, there's PDFs, there's PDFs, and the best feature I like is because I can add a PDF over here. So usually what I'll do is I would I'll drag and drop something. So suppose
This is
I
really
want to
spectacular.
download. Suppose I have my thermodynamic slides over here. Um I drag and drop it in. So let me just do this. So I would, over here, I would drag and drop it in, perhaps into the thermodynamic folder over here. Yeah, and then it'll be here, and it'll take a while to synchronize. So yeah, now it's uploading. You can see over here synchronizing, and this takes space though, so that's what I paid for. But the first like 200 megabytes of 300 megabytes are free or something. I upgraded it to 2 gigabytes, and if I remember correctly, it was only $10. It was really it wasn't expensive at all. Let me find the price. So Zotero price. Yeah, $20 a year.
Holy
So
hell.
yeah.
That's like a coffee every 3 months. What the hell? Oh
Yeah,
my God.
and it's free for the first 300 megabytes. So I used it up, and then I mean I decided that the cost of setting up my own is not worth the trouble. And I like it
Right.
because right now, if it synchronizes up, then that means I can go onto my phone, and yeah, I can download on my phone, and I do a lot of this switch around and stuff. Yeah, that's the main feature, I would say, being online and accessible.
Right. Oh my God, that is quite cool. That is cool.
And the
Yeah.
simple reason is because also because on the phone itself, they do scrolling. So for example, if I'm studying a very long book, annoying aspect of opening PDFs is that if I scroll to some very, very far away page, right, like halfway through the entire thing, on phone you have a nice scroller also. Let's say I'm over here. If I close it, and I open it up again, it returns back to that page. You can do notes and stuff, but I don't really use that feature that much. Because I prefer to I don't really take notes like this, but you can. I think the page thing, it matters a lot to me because I can be reading about this on my laptop in the day, and then later when I'm on the train, perhaps I want to read about it again. So I'll just scrolling spends a good like 20 seconds, and it's just a small annoyance. Yeah.
Right. Yeah, this is all very cool. Um,
Yeah, so I found that this is cool
right.
personally. And there's even a
Well, that's a yeah.
web plugin where you can there's even a web plugin where you can let me see if I have the plugin. I don't think I have the plugin over here, but there's a plugin Zotero. Um
Oh yeah, I used the plugin too. It's really
yeah, you can
nice.
use that. Do you use it at the moment or no?
I use it all the time.
Oh, cool.
Yeah, this is really something. It's really making things easy.
Yeah. Okay, cool. Is that all we have for today?
Yeah, pretty much.
Okay,
Yeah, that was
cool.
good.
Yeah, thanks
See you
for sharing
next
about
time, I guess.
yeah. See you Taeyun. Yeah, thanks for
I'll
joining.
see you, Chen Hao.
To see you sometime again soon. Bye.
Thank you for the great lecture about the statistical mechanics.
Thank you. Okay.
I'm gonna head out. See ya.
Have a nice day. Bye.
Yeah. Bye.